Today we'll show how to compute the net electric field for charges spread uniformly on a plate. Let's remind ourselves the recipe for carrying out this calculation. First, we're going to divide the plate into pieces. Now, in examples from previous lectures, the pieces were chosen so that each piece could be treated as a point charge. For the plate, we are going to choose charged rings as the pieces and use the result for the electric field of a charged ring that we derived in an earlier lecture. Now, the last step will be the same. We'll use the math expression for the typical piece, charged ring, and we'll use that to sum the electric fields for all the pieces. Now, the summing process can be done both analytically or numerically using a computer, and we'll do both in this lecture. First, let's do a demonstration of the numerical calculation, which will allow us to visualize the calculation process. Step one is, as we said, to divide the plate into pieces which will be concentric charged rings. Now, step two is to write down the expression for the electric field for a given piece. Here we're going to use, as we said, the earlier result for finding the electric field of a ring on the ring's symmetry axis. Since all of the rings we'll use are concentric, all the rings will have the same symmetry axis. Also, let's remember that on the symmetry axis, the electric field of each ring is parallel to that axis. Finally, we compute the electric field for each piece and add up the contributions. In the computer program, we're doing that one ring at a time. We started with the ring in the center. The red arrow shows the total E field so far. So as we visit each piece in turn, we find additional contributions. The red arrow changes as we continue to add the E field contributions of other rings. Finally, the red arrow shows the net electric field due to the plate at the observation location on the symmetry axis. Specifically, on the axis that passes through the center of the plate perpendicular to the plane in which the plate lies. For our choice of coordinate system, that symmetry axis is the z-axis. On this axis, the total E field of the plate is parallel to this axis. That is, only the z component of this net field in general is non-zero. We'll now use these insights from this numerical calculation to guide an analytic calculation of a charged plate's electric field on this symmetry axis. Let's consider a plate of radius capital R that lies in the xy plane with its center at the origin. Let's assume a total positive charge, capital Q, and assume that this charge is spread uniformly on the plate. Let's calculate the electric field at an observation location at coordinate z on the z-axis, the symmetry axis. Step one, we will break up the plate into rings. Let's focus on a typical ring like this. The ring has radius r and carries a charge delta Q. The ring also has a thickness delta R. Step two, we need to come up with a math expression that describes the E field of this typical piece, the E field of the ring at the observation location on the z-axis. We already have that from an earlier lecture. Let's call that expression delta EZ, the ring's electric field contribution to the net field of the charged plate. To use the expression for all the rings, we will need to find an expression for delta Q, the charge on a given ring. We will assume the plate is uniformly charged. That means the ratio of the amount of charge on a piece of plate to the area of that plate must be constant. And by taking the ratio of the total charge Q to the total plate area, pi times capital R squared, we know what that constant is. That means the ratio of the charge delta Q to the area of the ring must be equal to that same constant. Note that the area of the ring is just length times width. The length the circumference of the ring, 2 pi r, times the width of the ring, delta r. We can use this expression to solve for delta Q in terms of delta r. Let's substitute this result into our expression for delta EZ. We're going to pass over to the limit of very small pieces. That is, delta r becomes dr, and delta EZ becomes dEZ, the z component of an infinitesimally thin charged ring of radius little r, as shown here. We're now in a position to do this final step. Sum up all the E-field contributions of all the concentric rings that make up the plate. To do the sum, we can now integrate with respect to small r for ring radii ranging over the limits 0 to capital R. Now this integral can be done by substitution with this result. Now let's note the area capital A of the plate is pi times capital R squared. So let's put that in and multiply through by z to get this final result. This is the E field of a uniformly charged circular plate at an observation location on the symmetry axis, a distance z from the center of the plate. Let's look at some limiting cases for this result, which we can rewrite a bit like this. First, let's look at observation locations far from the plate, that is, for z much larger than capital R. In that limit, the electric field of the plate can be written to a good approximation like this. Here we've written out the plate area explicitly. The first part of the bracketed expression is the same, but the second part shows the two leading terms in the Taylor series expansion. When we simplify this, we end up with the point charge formula for the electric field. That is, when we are far enough from the plate looks like a point charge to a good approximation. Now let's look at the opposite limit, where z is much smaller than capital R. That means we're very close to the plate. In that limit, the first part of our expression is the same, but in the second part, we can ignore z in the denominator. If z is small enough, we can neglect the second part completely and end up with this result, which tells us that sufficiently near the plate, the electric field is essentially constant. This result holds even when we are not on the symmetry axis, as long as we are both near the plate and not too close to the edges of the plate. In a later lecture, we will use this result extensively to describe an electrical circuit element, the capacitor, which has countless uses in modern technology. For now, though, that's it. In our next lecture, we'll use the ring result to find the electric field of charged spheres.